and sharing my screen. And you guys are sure you're all right with the current pacing?
Mm-hmm.
Not too slow, not too fast.
No.
Okay. Then all of this stuff that was supposed to have been due on the 17th, including the activities, I'm going to move to the 22nd. Which, so instead of having them due next Wednesday, they'll be due the following Monday. Because of this time constraint, I'm going to ask that you start the activities on your own. I'm not sure that we're going to have class time for the activities. So as I'm saying that, I'm feeling a little bit remiss. So I'm going to real quick open my activity manual and just real quick see what words of advice I have for you on those first 4 activities. For activity 1, you're trying to draw angles. My suggestion with that one is you're not going to use a protractor, but rather you're going to remember that all the way around a circle is 360 degrees. And you're going to divide that up because those dots are evenly spaced. For activity 2, you do need a protractor. You do need to draw the triangles. And for activity 2, I want you to submit the drawings of your triangles. Activity 3 just makes use of what we were talking about with the Jordan closed curve theorem and determining whether things are interior or exterior. Activity 4 asks you to use your pattern blocks. They're like the, oh, you think I'd remember the colors. I think the green triangles and the blue squares and the red trapezoids and the yellow hexagons. With those, in the space provided, you have to show your diagram, show a drawing of what you did. So please make sure with each of those that you don't just answer the questions, but you show your work, you show your drawings, you submit your drawings that you use for each.
The pattern blocks are in the back of the book?
Yeah, they're punch out pattern blocks in the back of the
Okay.
book. They're in a like a Ziploc thing. I know that when I taught 108 last semester, I pulled all mine out and punched them out, but they're like punch cards like this. You might have used those in 108 looking at fractions. Do you remember doing fractions with the pattern blocks? And like if you looked at the hexagon as a whole, a triangle would have been a 6th and so on. So those of you who had me for 108, I hope you remember that. Those of you who had Mr. Milazzo for 108, I'm not sure if he did that or not, but hopefully you can kind of wrap your minds around it. Any other questions on those? If not, then
No, I don't think so.
okay. And next, I'm going to go to the internet. I'm going to go to my labs. In my labs, let's see if I can remember where I put this. I'm going to go to Learning Modules Content. And in Learning Modules Content, I had uploaded yesterday a virtual protractor because I know a couple folks said that they weren't real good with using a protractor. And so not the best virtual protractor, but the only one that I found that I could use now in class to kind of show. So in order to use a protractor to draw an angle, what you're going to do is you're going to put the protractor so that the point of the protractor is on the vertex of where the angle is. We're not doing construction, so we're going to stop there. You're going to put the point of the protractor so that it's on the corner, and then you're going to go to where that measurement is and draw your angle. What I think makes it a little dicey for some people is as I look at this protractor, you might notice that it's got two number scales, one that starts at 0 on the left and one that starts at 0 on the right. And which one you use depends on which way you're drawing your angle. My suggestion and their suggestion is to, before you begin, decide whether you want whether your angle should be smaller than 90, an acute angle, or bigger than 90, an obtuse angle. And if you put the 0 line and the point here, if I'm drawing an angle from here, I'm going to use the scale that counts up from 0. Instead, let me do a different color angle. Instead, if my 0 line is here and my vertex is here, then I'm going to use this inner scale that counts up from 0. In terms of measuring an angle, I always forget when I'm doing this to turn my finger from pen to mouse. Let's say I'm going down here and I want to find the measures of these angles. Of course, now none of them are going to be user friendly because this computer doesn't have the arrow buttons for me to rotate it. And when yeah, this one does. Damn it. My arrow, I don't have all the arrow buttons on this keyboard. Okay. So what I have to do is I have to take my protractor and, oh yeah, this is letting me use the arrow buttons. Rotate it. And what I want to do is I want to place my protractor, if I'm measuring angle B, so that the dot is on the B and the segment CB is along that line from 0 to the dot. And before I begin, I'm going to look at it. And does everybody realize that angle B is smaller than a right angle? So I want to use the scale that gives me an acute angle and measure no angle less than 90. So now I'm going to move this and I'm going to put it so that the vertex is at B. And I think I have to move it just a little bit so that it lines right up. Do you see how 0 is lined up? And now, because it's an acute angle, I'm going to use the scale that gives me the measure of 30 degrees and not 150 degrees for angle B. Instead, if I wanted to measure angle C, I'm going to move it so that the vertex is at C. Again, that side should be lined up so that the angle goes right through the 0 line. And now for angle C, do you see it's, I apologize, before we begin, does everybody see it's less than 90? So now I'm going to put this up here on C, and I'm going to use the scale that makes that less than 90. I'm going to follow through. And does everybody see that it would be partway between 50 and 60? This protractor isn't all that accurate. I would say that it's probably about 52. If it were the obtuse angle on the other side, then I would be going between 120 and 130. But this one's obviously acute. Does that help with folks who said that they weren't real comfortable using a protractor?
Yeah.
Okay. So, and again, in terms of, I know that some people where the point of confusion is, hey, there's two numbers there, which one do I use? And my suggestion is before you put that protractor on that angle, ask yourself, is that angle smaller than a right angle or bigger than a right angle? If it's an acute angle, if it's smaller than the right angle, use a scale that gives you the number less than 90. If it's bigger than the right angle, use the scale that gives you the number over 90. All right?
Mm-hmm.
Okay, and so that's that. Let me get rid of that toolbar. I think that'll be out of the way up here. And so now we looked over here and changed those due dates. And I apologize about not having class time to work on those activities. But again, if you have any questions on them, please, 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 please ask. Before we pick up with the notes, did anybody have start looking at those activities and have questions on any of them?
I have a question on the homework.
Thank you. You're a mind reader. That was where I was going to go next. If you don't have a question on the activity, do you have one on the homework? You're amazing. You've read my mind. What page and what question number?
Number 27 on page 459.
I was so afraid that the book wasn't going to work for me because I opened it before we began class and it's been idle for a while. I might have spoken too soon though. Which question number, hon? 27?
27.
Okay. Okay. Question number 27. I love this question. And this is along the lines of those pattern blocks that are punched out in your book. It says the interior angles of pattern blocks can be investigated by creating designs such as the one shown here. And so now you want to explain how you can use these designs to determine A, the measures of the equilateral triangle. Well, over here, as I look at this equilateral triangle, can you guys see my cursor moving around or not?
No.
Okay. Then I guess I'm going to use a pen. As I look at the angles of going around here, we know those all are the same. We know that all the way around a point is 360 degrees. And how many triangles fit in there?
6.
6. So wouldn't each angle be 360 divided by 6? And that'll give you your numeric answer. In the same way here, wouldn't we take 360 and divide it by 4? And in the same way here, wouldn't we take 360 and divide it by 3? So far, so good.
Mm-hmm.
And that's part of what that activity, I think it's activity 4, asks you to do. Now I'm going to clear those. And I'm going to go down here and look at this next one, the trapezoid. If I actually, and you actually have those blocks punched out, if I actually had those blocks punched out, I would notice that I could take this figure and those two trapezoids would fit right on top of one of my hexagons. And so wouldn't that tell me that, I apologize, wouldn't that tell me that this angle of my trapezoid would be equal to each angle of the hexagon? And wouldn't it tell me that this smaller angle of the trapezoid, well, wouldn't that be half of the angles of the hexagon?
Mm-hmm.
And then in that same way, this figure with the 4 blue rhombuses I believe that figure should also fit right on top of my hexagon. And I can use that to find those measures. And then over here, this last one, well, we can use the fact that we know this angle is 90 from the squares. We know the measure of this angle from the rhombus, and so we can find the measure of this angle by subtracting from 360, and so on. And so by piling those different shapes on top of each other, we can use what the angles add up to. I do believe that if you take those three figures and stack them the way they're shown, you'll find that this angle up here is also going to be the same as the angle of the square. And so it's using the manipulatives instead of math to come up with those measures by stacking figures on top of each other to find out what the angle measures are. Does that help?
Kinda.
And I can very easily picture this being done in elementary class, where you give, if we were on campus, I have a great big tote class set of foam, these shapes, and doing the activity, I would have passed them out and actually in class, looking at this problem, I would have pulled them up in front. If it's still not clear, I will make myself a note right now to pull up the virtual pattern blocks, and we can revisit this question with those virtual pattern blocks on Wednesday. Okay?
Okay.
Any other homework questions? Megan, I got you on the attention line. Thank you.
The one that it says, I'm trying to find it. We have to measure. Trying to find it. It says user for question for page 440. It says use a ruler to measure MA and MB.
Mhm.
What can you say about point M?
Mhm.
Does it have to be inches or centimeters, or does it not matter?
It does not matter. And
Okay.
on that page with that question, I know it's with the two overlapping circles, right? Over here, this picture in the textbook is super tiny. Redraw it, and when you redraw it, make sure your circles are round. So for example, for that picture on my paper that I'm doing my activities on, I would draw, trace round cups or something like that to come up with my circle.
Yeah, I used 2/4. I just wasn't sure if I had to like use centimeters or inches.
No, and actually, what we're looking for is the length of AM and the length of MB. And so let's do a little bit of not as precise reasoning. Looking at that picture now, what do you think is going to be true about the length of the distance from A to M and the distance from B to M?
They're going to be equal.
Yep. And so what will we be able to say about M?
M is half of A, which is half of B.
Oh, or M is in the middle, or M is a midpoint, right?
Mm-hmm.
Using those big kid words, right? So, okay, better?
Mm-hmm.
With this one down here, use your protractor to measure those angles. Use your protractor to measure those angles and draw those conclusions. Because folks, I'm not stupid. I know the answers to these questions are in the back of the book. I want to see how you got those answers. I think previous semesters, I had some people who just copied all the answers out of the back of the book. And I can tell, and you get 0 credit for that, okay? If all I have is a sheet of paper with the answers from the back of the book, you're not getting nothing. I want to see your work. I want it in your own words. And I am positive the way you would paraphrase a situation and answer a question is not word for word identical to what the author of the book would say. Or even if you're working together with somebody on the homework, I'm positive that two people will not write word for word an identical paragraph. And so if I have two paragraphs that are word for word identical, nobody's getting credit for them. Okay? I digress. Any other homework questions?
And that was all the ones I had.
Okay, how about anybody else? Not hearing any. I'm going to pick up from where we left off. I think we left off, we had filled in page 10 with the different types of triangles. And so after we look at those different types of triangles, the next thing that we're going to look at on page 11 are the different types of quadrilaterals. And again, we had said quadrilaterals have four sides. The author of the textbook talks about a kite, and they say that a kite has two pairs of congruent adjacent sides. And has anybody ever flown a kite? You know, I don't know, is anybody else a big Mary Poppins movie fan? Like the kites that they fly at the beginning of Mary Poppins, where these two sides are congruent, equal length. These two sides are congruent, equal length, but the red and the blue sides aren't necessarily congruent to each other. Because it's a quadrilateral, the angle sum will be 360 degrees. And it turns out that in a kite, these angles are congruent, but the other pairs of angles are not.
How are the top and bottom not congruent?
Let me try to draw a more exaggerated kite. Let's say these are like this, and this is like this. And so now looking at that picture, is it more obvious that this angle and this angle would definitely have different measures?
Yeah.
I'm sorry, I wasn't real good at drawing my kite, but let's put a tail on it just for fun. Never mind. So, okay, trapezoid. I differ with the authors of your textbook. Your textbook is the only source where I see their definition of a trapezoid. They say a trapezoid is a quadrilateral with at least one pair of parallel sides. Every other book that I've ever seen says that a trapezoid is a quadrilateral with exactly one pair of parallel sides. And so I'm going to work with this definition instead of the author's definition. Most math sources say that trapezoids have only one pair of parallel sides. So over here, I'm going to try to draw a pair of parallel sides. And I'm not real great at drawing. And we'll call this TRAP. And so TR in here will be parallel to AP. Because they're parallel, I picture this parallel line extending and this parallel line extending. Can I look at this as a transversal? And so what happens are those two angles, angle T and angle P, will be supplements because of their relationships within the parallel lines. Likewise, angle R and angle A will be supplements. So that this angle and this angle are supplements. But angle P doesn't necessarily have a specific relationship to angle A. There is one type of trapezoid that you focus on a little bit more, and that's an isosceles. I misspelled it. ISOSCELES trapezoid. And in isosceles trapezoid, the non-parallel sides are congruent. Are you guys all right if I use the congruent symbol instead of writing the word congruent?
Mhm.
And so over here, I'm going to draw another one. And using my infinite creativity, I'm going to call this one ZOID. So we have trapezoid. ZO is parallel to ID. And so DZ is congruent to OI. And what happens, these angles are considered base angles, and they turn out to be congruent if it's isosceles. So we'd be able to say that angle D is congruent to angle I, and also that angle Z is congruent to angle O. And I have to apologize, I used that term base, and I didn't label that on the preceding picture. The parallel sides are called the bases. Oh, Lord. The parallel sides are the bases. The non-parallel sides are the lengths. Another thing that turns out to be kind of cool with an isosceles trapezoid is that the diagonals are congruent. An interesting sign. Everybody comfortable with trapezoids? One pair of parallel sides. Back in ancient times when I taught high school math, I had some students tell me that the trapezoid was the dog bowl. And I guess I can sort of see some dog bowls have that shape, right? So a parallelogram is going to be defined a little bit differently. A parallelogram is, again, four sides, a quadrilateral, with two pairs of parallel sides. So if I picture these sides will be parallel, and also these sides will be parallel. So I guess we'll call this GRAM. So GR is parallel to AM. RA is parallel to GM. And this is where the author's definition differs from everybody else's, because the author then says, well, a parallelogram, can be thought of as a trapezoid, Because if it has two pairs of parallel sides, then it has to have at least one. And I have never seen any other resource that said that a parallelogram is also a trapezoid. What's cool is because of the alternate interior angles, this angle and this angle, I'm sorry, interior angles on the same side of the transversal, those two angles would be supplementary. But then because these are parallel, this will also be a supplement of this. And this will be a supplement of this. And so that gives me the idea that opposite angles are congruent. So we'd be able to say, for example, angle M is congruent to angle R, and angle G is congruent to angle A. And we'll find out later on in chapter 11, when we start looking at verifying and proving things, that opposite sides are congruent. So that segment GR is congruent to segment MA, and also segment GM is congruent to segment RA. They'll have the same length. And also, if I go through and I draw my diagonals in a parallelogram, we're going to find that the diagonals bisect each other. And again, that means that they split each other in half. They have the same midpoint. And so there's a lot going on with that parallelogram. Opposite sides are parallel, opposite sides are congruent, opposite angles are congruent, and the diagonals cut each other in half. Parallelogram, okay. You really have to have a good handle on parallelograms to understand the next four. Next one, whoops, page 12, is a rhombus. We're going to define a rhombus as a parallelogram. I am sorry. I must be Friday tired. Every word I start trying to write and spell wrong. And I know it too. A parallelogram with congruent adjacent sides. So I want to draw a parallelogram where I know that two sides next to each other have the same length. I'm going to call this RHOM. Because it's a parallelogram, I know that RH is parallel to MO. I know that RM is parallel to HO. By definition, I know that RH is congruent to RM. But now wait a minute, because it's a parallelogram, isn't RM also congruent to HO? And isn't RH also congruent to MO? And so all four sides are the same. So it's an equilateral quadrilateral. And again, all of the other parallelogram properties hold true because it is a parallelogram. Sides parallel, opposite sides congruent, making all sides congruent. And also, I think we had said in a parallelogram that those opposite angles are congruent. And we had said in a parallelogram that those diagonals have a common midpoint. They bisect each other. And another thing that's kind of cool about the diagonals of a rhombus are that the diagonals bisect the angles. And so, like over here, I'm taking angle O and dividing it into 2 equal parts. I'm taking angle H and dividing it into 2 equal parts. And if I look at any one of those triangles that are formed then, what's really cool, well, if this angle and this angle add up to 180, their halves have to add up to 90, which means this angle in here has to be 90. And so the diagonals are perpendicular. How fun is that? Everybody all right with what a rhombus is? If so, our next figure is a rectangle. And we're going to define a rectangle as a parallelogram. And so in saying that it's a parallelogram, opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. But what's special about a rectangle is it's a parallelogram with a right angle. And so by this definition, it's a parallelogram that has a right angle. So I'm going to draw one side, then I'm going to draw in my right angle. Now these opposite sides have to be parallel. These opposite sides have to be parallel. Well, if this is a right angle, let's name this guy RECT. This is a right angle, then this is a right angle. And if these lines are parallel, these angles have to add up to 180. And so those angles are also right angles. And so because of the angle relationships in a parallelogram, if it has one right angle, it has all right angles. And so we can say that it's equiangular. And again, because it's a parallelogram, besides the angle relationships, the opposite sides are congruent. And if I go through and draw on my diagonals, if I look at this diagonal, you see the triangle that forms. And if I look at this diagonal, if we see the triangle that forms, those two triangles turn out to be the same. And that means that the diagonals are congruent. So a rhombus is a special type of parallelogram. A rectangle is a special type of parallelogram. Which leads us to our last one, which I'm guessing you folks can predict, is, whoops, where did I go? I just totally picked the wrong page number. A square. And a square can be defined in one of two ways. A square is a rectangle with congruent sides. Or a rhombus with right angles. And either definition, a rectangle is a parallelogram, and a rhombus is a parallelogram. So a square is a very special parallelogram. It's a parallelogram, so opposite sides are parallel. It's a rectangle, so it has right angles. It's a rhombus, so all of the sides are congruent. Let's call this SQUA. Because it's a rhombus, the diagonals bisect the angles and are perpendicular. And because it's a rectangle, the diagonals are also congruent. Because it's a rhombus, it's equilateral. All the sides are equal. And because it's a rectangle, it's equiangular. All the angles are equal. And so that's like the favored child. It's got all of the graces. It has all of the properties of all of the other parallelograms. How fun is that? Is everybody familiar with squares and all of the magic properties they have, special properties they have? Can I move on? Are you guys all right? Not hearing any questions. Then next definition that we have is that of a regular polygon. And a regular polygon is a polygon that's both equilateral and equiangular. All of the sides are equal. All of the angles are equal. Since it's both equilateral and equiangular, we could say that a regular quadrilateral is a square. A regular triangle is our equilateral triangle. Now, in terms of each interior angle, well, if my regular polygon has n sides, the sum of the angles is 180 times n minus 2. And if it has n sides, it has n angles, and they're all the same measure. So I'm going to divide that 180 times n minus 2 by n. So for example, let's have you folks find the measure of the interior angles of a regular hexagon. And I'll give you folks a minute to do that. Did anybody else get 120 degrees? And in the same way, you should be able to use this formula backwards. And if I had that 120 degrees, I should be able to take that 180 times n minus 2 over n and set it equal to that 120 and cross multiply the sum. Each exterior angle, if a regular polygon has n sides, the sum of the exterior angles is always 360, and we're going to divide it by the number of angles. So the exterior angle of a regular hexagon would be, let's see, 360 divided by 6, or 60 degrees. Now I want to ask you a question. Which formula did you find easier, the interior angle or the exterior angle?
Exterior.
Exterior, and I'm with you on that one. So, could I, do you notice that the exterior and the interior are always supplementary? And so if I wanted to, could I always find the exterior angle first and then subtract from 180 to find the interior? So for example, if I have a regular pentagon, even if I wanted the interior angles, it's probably easier to say the exterior angle is 360 divided by 5, or 72. And so the interior is 180 minus 72, or 108. And sometimes I think, if, which I'm going to ask you, if I tell you how big the interior angle is, and I want to know how many sides I have, I think it's easier to take that interior angle, find its supplement, and then divide 360 by that number to get the number of sides, as opposed to using this other formula. And you'll see those types of questions in the homework. Central angle, I'm going to try my darndest to draw a regular hexagon. Central angle, I'm going to take a point in the center and connect it to each of the vertices. And does everybody see that those would all be equal? And so each central angle is the total of the angles divided by how many. And so the central angles are going to be equal in measure to the exterior angles. And then just real quick. Oh, we didn't do circles yet. Oh dear, Wednesday we're going to have a lot to do because we're going to have to look at circles and also space figures. But over the weekend, if you have a chance and you can look at these circle definitions, it'll make our life a little bit easier and give you a little bit less writing to do on Wednesday. I'm looking at my clock and it's that time already. Is it me or does class seem to go too fast? Or is this like, are you guys like in tears, bored, and it's taking forever?
It seems to go by fast.